if you are given some FA, finite automaton, then how you can construct or how you can check whether the given FA has minimum number of states or not. If your input is FA, you are giving you are given some FA, you have some FA, and you want to prove whether this has the minimum states or not. FA, you have the question. If somebody gives you FA, then he may question that can you identify this FA has minimum number of states? And if you identify that okay, this is not having the minimum number of states, then actually you need to construct the FA that should have the minimum states. So how would you know if somebody gives you FA? How would you know that the FA has minimum number of states or not? So one way to prove whether the FA has minimum state or not, you need to identify the equivalence classes your FA is going to accept. And if the number of equivalence classes and number of states in your FA remains same, then you can say that your FA has the minimum number of states. Means you can you have some FA, you are given some FA which may be accepting the language L. For the language L, you are given some FA. And what you need actually, you need to identify on behalf of this language L, how many equivalence classes, how you can partition the set. You have the set sigma star, and sigma star contains all possible strings. So you know that for some strings your FA goes to one place, for some other string your FA may goes to the different places. So try to find out the equivalence classes on sigma star with respect to the language L. And if number of equivalence classes you have found, you have identified, and the number of states in your given FA are same, then you can say that the FA has minimum number of states. So how could you identify like this? So the one way is to, you can, for the given FA, you can partition the set sigma star according to the states of the FA. You have the language. For this language, we have the FA like this. So this is the FA. So see, whatever input you can supply from this set, if somebody asks you that, okay, this is the FA, and I am interested to know whether this has the minimum state or not. So how would you know that this FA has the minimum number of states? So you know that in this FA, starting from the initial state Q0, you can supply any input from the sigma star. And on supplying any input from the sigma star, your FA will go to any one of these states. So your FA goes to different places on different kind of strings in the sigma star. So you see that you can partition the set sigma star according to the states of this DFA. So how you can partition? See, we have the set, and what we mean that this is represent all possible strings sigma star in this set. So how you can partition the sigma star, because you have all possible strings in this set, and you need to partition the sigma star on behalf of the given FA. You are given the FA like this. You have the FA like. So how you can partition? This means what? What is the language? See, whenever your FA ends in the Q5, in this state Q5, and this is what? This is the final state. So what is the language you are going to accept? Means you have the X ends with 10. This is the language we are going to accept. Means the language of Q5 is what? 10. Whenever your FA ends in Q3, then what is the language you are going to accept? Every strings that ends with 00. If you are at Q4, then if you are ending at Q4, this means you are ending for all possible strings that ends in 10. So we have, if you are at the, if your FA ends in the Q0, it means your input is what? Null. So you are starting from the Q0 and your input is null. So language of this Q0 is what? Null. So you can say, you can partition the set. So, sorry. If you are ending at the Q0, the language of Q0 is what? This is accepting the null string. So see, if you have the null strings and this is the start state, then where you are ending, your FE stops at Q0. Once your FE stops at Q0 means what language you are going to accept, you have the null. If you just have the 0 only, so on receiving 0, your FA goes to the Q1. So your FA ends in Q1 means what kind of language you are going to accept in the Q1? Only 0. So the language you are going to accept at the state Q1 is what? You are accepting only 0. This is the language. And if you are ending at the Q3, the language you are accepting at the Q3 is what? All set of strings that ends in 00. So you have 0, 1, clean star, and 00. This is the language you are going to accept at the Q3. Similarly, if you are having the Q5, what kind of language you are going to accept? We know the language. So this is the language at Q3, and you have the language at Q5, which is what? 0, 1, clean star, and you have the 1, 0. String ends in 1, 0. Q5 is the final state. This is the final state. And whenever you are at the Q2, what kind of strings you are going to accept? So language at Q2 is what? You are going to accept the language only this, right? Whenever you are at the Q4, what kind of language you are going to accept? So language at Q4. So language at Q4 is what? All possible strings that ends in 0 and 1. So here you can say all such strings 0, 1, clean star, and which ends in 0, 1. So this is the language you are accepting at the Q4. What is the language you are going to accept at the Q6? So language at the Q6 you have is all possible strings that ends in 11. This is the string. So you have the partitions. This you are going to partition the set like this. So you have the partition here. Okay. So you find that this is one set, this is other set, okay, and this is one set of strings, and this is you have the other set of strings, and you also have this is one set of string, and this is so they see with respect to the given FA, you have partitioned the set sigma star in this kind of situation as with respect to the states of your FA. Now these are the only possible strings in the sigma star. So all possible strings are here. Now question is we have partitioned the sigma star with respect to the states of the DFA. Now what you need to partition the set sigma star with respect to the equivalence classes. So you need to identify what are the equivalence classes. So see that in your FA, for the case of null string, on receiving the null string, your FA goes to the Q0. On receiving the string 0, your FA goes to the Q1. Means your FA tries to remember the null string and your FA tries to remember the string 0. And also for all such string it goes to the Q3. This means this set of strings your FA is going to remembering as the different as this set of string. So you have constructed the FA like this. So with respect to the given language L, we have the language L. You need to really know that do you is this okay for the FA for remembering all such kind of strings. So how would you identify actually? You need to identify with respect to the equivalence classes. So try to see you have the strings null here and you have the string 0 here. So here you have the null string, say for example x is equal to null and you have y is equal to 0. So if your FA should go to the different states if and only if x and y are distinguishable. We know that. So can you find any z which is taken from the sigma star so that you can distinguish x and y, means so that you can say that xz is in the language and yz is not in the language, or yz is not in the language then xz is in the language. So you can take any strings. So if you take z as, say for example, if z is equal to 1 0, so xz is what? Xz becomes this and yz becomes 0 1 0, and this ends with 1 0, this ends with 1 0, both belongs to the language. So you can sorry, you can say that x and y are not distinguishable here. So question is that you may have some other z, so try to identify the other z. So what happened, either any strings you can take, say the string that ends with 1 0, all such strings which ends with 1 0, if you z can be taken all such strings which ends with 1 0, then on concatenating with x and y you will find that xz is the language and yz also in the language. If you are taking all string, z can be taken all possible strings for which it ends in 00, then you also find that if you concate with, if z is all strings that ends with 00, means all string which ends with 00, then what happen? This ends with 00 means xz and yz. Xz and yz. Xz is not in the language and yz also is not in the language. So you are not going to say that one is in the language, another is not in the language. If you take any strings that ends in 0 1, then also xz, once you say xz, then it ends in 0 1. If you say yz, then also it ends in 1 0 1, and both are not in the language. So if you take the string like this, it's 1. So x, here you have the 1 and here also you have the 1. It means xz and yz both are not in the language. So if you take z as 0 also, if you take 0 also, if z is 0, then xz and yz both are not in the language. So you see that for every possible z taken from the sigma star, you are not able to distinguish the strings null and q0, and hence null and 0 cannot be distinguished, means null and 0 are equivalent. If you are not able to distinguish, means null string and for the string 0, your FA should not distinguish actually. It means for all such string it should go to one place, means they come in one equivalence class. You are not going x and y, you are not going to distinguish, and this is in one equivalent class. So you can also find, can you distinguish the strings from LQ1 and LQ3? You know that you cannot distinguish this and this. So if you can take any strings x, say 0, and LQ, from LQ you can take y, any string that ends in 00. So you have the situation, you can take z that ends in 00. If it ends in 00, means xz and yz both are in language. If z ends in 11, You are taking the z which ends in double one, then this is not in the language. Xz is not in the language. Yz also not in the language. If z ends in 0 1, then xz is not in the language. Yz is not in the language. If z is 1, then this is xz 0 1 and yz means 0 0 1, not in the language. So 1 0, then xz, if you take z that ends in 1 0, then xz and yz both are in the language. So either both are in the language and both are not in the language. So actually you are not going to distinguish LQ1, the set LQ1 and LQ3, and you are not able to distinguish LQ0 and LQ0 and LQ1. So LQ0 and LQ1 you are not going to distinguish, means null and 0 you are not going to distinguish, means they are equivalent classes. Null and 0 are related with equivalence relations, and since 0 and the strings from the LQ3 are also not distinguishable, so you can say that the string from the set LQ is also not distinguishable with the set LQ0. Means all such strings are actually not distinguishable, and hence this is corresponds to one equivalence classes. So this is for all such strings, your FA should not go to the different place. These are all one equivalence classes you have. So you can see that this is one equivalence class you have. So this is the partition you have made. Now this is the one partition you have found. This is one group you have found with respect to the relationship equivalence relations. So this is so, and you find that all such strings are in one equivalence classes. So if they are in one equivalence classes, you don't require to transit, you don't require to, your FA should not go to different places. Now you can also, similarly, you can also find that the string 1 and the string from the set LQ4 are distinguishable, are not distinguishable. So you will say that the set the string from the set LQ2 and the string from the set LQ4 cannot be distinguished. Why it is so? Because this ends in 1 and this is also ending in 1. So any z you can take that ends in 1 1, then both will not be in the language. Or any z you can take that ends in 1 0, then both are in the language. Or any string you can take that ends in 0, then what happen? If you take z as 0, then 1 0, here also 1 0, both are in the language. If you take the strings z as that ends in double zero, then you will see that on concatenation you will find that 00 will be at end. Here also 00 will be at end. Both are not in the language. So strings from the set LQ2 and LQ4 are also not distinguishable, and hence they are in one equivalence class. Now you can similarly you can also find that the set of strings from the LQ4 and from the LQ6 are also not distinguishable. So any strings you can take which is ending in 1 0 1, here it is ending in 1 1. So any set you can take, you will find that either both are in the language or both are not in the language. So LQ6, any string from the LQ6 are also not distinguishable with any string from the LQ4. So you will find that this is also one equivalent, but you can say you can distinguish the string from this set and this set, means LQ0 set the strings from the LQ0 and LQ2 you can distinguish, like here LQ0 contains null string and LQ2 contains the string, say y is equal to, here you have the 1. So if you are going to distinguish, then you have some z which is taken from the sigma star, and you can take here z is equal to say 0, and once you concate xz, so you will find that xz becomes 0 and yz becomes 1 0. This is in the language and this is not in the language. So this says that you can distinguish x and y. So hence you are going to distinguish this with this, and also means this is in one equivalence class and this is other equivalence class, means you are going to distinguish the strings from this equivalence class and in this equivalence. So this is in different equivalence class and this is in different equivalence. So the set of strings, the strings from the same equivalence class cannot be distinguished. Any two strings you can take from this set. Any two strings you can take from this equivalence class. Say this is the equivalence class B I'm letting, and this is the equivalence class A. So any two strings you can take from the equivalence class B, you cannot distinguish. Any two strings you can take from the equivalence class A, you cannot distinguish. But any two strings you can take, if any string you can take from equivalence class A and any string you can take from the equivalence class B, you can distinguish. Now you see that, can you distinguish the strings from LQ5 with LQ6? No, because this string ends in 10 and this ends in 11. If you can take Z as the null also, you can take null also. So exit, this is not in the language, but this will be in the language. So you can distinguish this with this. Similarly, you can the strings from the set LQ5. Any string you can take from the set LQ5, like x is equal to 10 simply. And any string you can take from the equivalence class A, like I am taking the string that is 00. And you can see that you can easily distinguish. You can take Z as null string. Z can be taken any string which is from the sigma star, and sigma star contains null string. So you say that xz is this and yz is this. This means this ends in 10 and this is not ending in 10, means this is in the language and this is not in the language. So this is the condition you can say, you can distinguish, and the null string is sufficient to distinguish x and y. So the strings from the set LQ5 and string from the equivalence class A can be distinguished. So this cannot go to this equivalence class, this is different. And also you can distinguish the string from the set LQ5 and the string from the equivalence class B. So like you can take x as 1x, you can take the string x you can take as 11. So you have x is equal to 11 from the LQ6, and you can take y you can take from the LQ5 as 10. Again, if you can take z as null string, z is equal to null, then this z is sufficient to distinguish. So xz and yz, this is not in the language, this is in the language. So you are also going to distinguish from the strings from this set and string from the equivalence class B. So this is the different classes of string. This set is different. So this is also one equivalence class, and we can say this is the equivalence class C. Now what happened with the help of the equivalence classes, you have partitioned the set sigma star. Okay, so we have partitioned the set sigma star, and you have partitioned the set sigma star, and you come to know that on behalf of the partitioning, on behalf of the states of the FA, how many partitions you have? 1, 2, 3, 4, 5, 6, 7, because you have the 7 state, 7 partition. And you have grouped the string. You have grouped means you have partitioned the strings on behalf of the equivalence classes, and you have found 3 different equivalence classes. So on behalf of the language accepted by the given FA, you find that the number of equivalence classes are 3, whereas the number of classes as per the states of the DIF is 7. So number of equivalence classes here for this language is 3. You have the 3 equivalence classes, but you have the 7 states in the DFA, and this shows clearly that the given DFA is not a minimum state DFA. DFA means deterministic finite automata. Once you say finite automata, we are talking about the deterministic finite automata. because from every state we mention clearly that for the input strings where your FA goes. So explicitly you are mentioning that for every input what is the decision your FA is going to take. So that's why this is the DFA case. If I say FA, you mean DFA means deterministic finite automata. Now you have made the decisions. Your input was the FA like this. You are given the FA and you were asked that whether this FA has minimum number of states or not. So what you have done, you have partitioned the set sigma star here. This is the sigma star, and on you have seen that you have partitioned the sigma star on behalf of the states of the DFA and on behalf of the equivalence classes, and you find that there are three different equivalence classes, and here you have the 7 states of the FA. So you come to know that the many states are unnecessary and you don't require to distinct, means for accepting the strings of all strings of this or all strings from this or all strings from this, means your FA should not remember all such string and hence it should go to only one places. This means for obtaining the minimum state DFA, what you need actually, you need to merge the states Q0, Q1 and Q3. You need to merge because you have seen that Q0, Q1 and Q3, your FA goes to 3 different places and they are in one equivalence classes. So what you need actually, whenever you are going to obtain the minimum state DFA, then you have to see that which of the states you need to merge. So how would you know? Here you have come to know that on behalf of the equivalence classes with respect to the language accepted by the FA, you find that all such set or the strings from this equivalence class, any two strings from this equivalence class cannot be distinguished, and hence on given of any such strings from this equivalence class, your FA should not go to different place. This means your FA has unnecessary more number of states and you need to merge the states from Q0, Q1 and Q3. Means you need to merge the state Q0, Q3 and Q0, Q1 and Q3. You need to merge to form one state. This is corresponds to A, say for example. Similarly, the strings from the set LQ2, LQ4 and LQ6 are not distinguishable, and this is, you have the one equivalence classes, class B. So since you are not able to distinguish any two strings from the equivalence class B, this means on applying any strings from the equivalence class B, your FA should not go to the different places, it should go only one place. So what you conclude that the state Q2, Q4 and Q6. So state Q2, Q4 and Q6 need to merge. So you need to merge the state Q2, Q4 and Q6 to form a one state. This is, you can form one state, say this is the state B, because this is corresponds to the equivalence class B. Now the strings, this is one equivalence class and this is the one equivalence class correspond to the state Q5, means for all such string that ends in 10, your FA must ends in Q5, and here Q5 is one equivalence class. So this is corresponds to C. So this is C. So in this way you come to know that by using the concept of the equivalence classes, you come to know that which states of your DFA need to merge and which is not needed to merge. So once you have this kind of observations, then you will be able to construct the equivalence classes. Question is that how you can obtain the DFA like this. You have the equivalence class A. You have the equivalence class A. And this is corresponds to one state. This is corresponds to one state. Okay. So now question is that whether this is the initial state of your FA or not. So how would you know? A is the equivalence class, and in A the string the string from the set LQ0 is there, and Q0 is the initial state here. So you can mention this as the initial state. Now you have to give the transition for 0 and 1. If you have 0, if you are receiving 0 here, then if you are receiving 0 here, so what you are going, the 0 is in the same equivalence classes. Actually you have the 0, so you have the q1. For 0 you are going to the q1, and since q1 and q0 you have merged, so actually you remain in the same place. Now if you are at the A and you are supplying the input, you are given the input 1. Now you see that if you have the input 1 and 1 is in the, you have seen that it is in the set LQ2. This is means this comes in the equivalence class B. So this comes to the equivalence class B. It means your FA should transit from this equivalence class to the equivalence class B. Whenever you are at the B, whenever you receive 0, so this is for the 1. Whenever you are at the equivalence class B and you receive 0, then what happen? You are having the 1 0, and 1 0, in which equivalence class you will have the strings 1 0 at the last, in the equivalence class C. So whenever you are going to receive 0, you have to go for the equivalence class C, and the equivalence class C should be the final state, because Q5 is the final state. Now if you are at the equivalence class B, you are receiving 1, so you are ending in 1. So strings ends in 1. In which equivalence classes? Every strings ends in 1. This is in the equivalence class B. So you are having you are in the same equivalence class. Now whenever you are in C and you are getting 0, then you will have double 0 at the last, and double 0 at the last, in where you are having in the equivalence class A. You have the double 0 in the last. So you, from this place, from this equivalence class, you can transit to the equivalence class A for the case of 0. Whenever you are at the C and you have the 1, then what happen? If 1 is there, then it ends in 0 1. And where you are going? 0 1 is in the equivalence class B. So from here you have to move at the B for the case of 1. If you have the 1 here, then it ends in 1 0. So 1 ends in 0 1, and 0 1 is in the equivalence class B. So this is the way you can give the transition, and hence this is the minimum state FA. So you did two work. One is you were given the finite automaton, and you needed to decide whether this FA has minimum states or not. So you have partitioned this at sigma star. Actually, as we know that we are going to partition this at sigma star, means we try to identify the strings in the sigma star which can be remembered. Means we are finding the groups. So one group of strings should be in one place. For one group of strings, your FA should go to the one place. That are the equivalence classes. So we have on given FA, according to the given FA states, we have partitioned the strings, partition the set sigma star, and by using the concept of the equivalence classes, you have made the partition, and you find that there are 3 equivalence classes, and you have the 7 number of states, and that's why your given FA has more number of states, and that it is possible to construct the FA less than that number of states. And actually, since you have the 3 number of equivalence classes, you can construct the FA having three number of states. And also we we know that it is not possible to construct the FA less than this number of states. So if you have for some given language, if you identify that the number of equivalence classes are, say, if you identify the n number of equivalence classes, then you can construct the FA for that language having the n number of states. It is not possible to construct the FA less than the n states. So since here you have the three number of states, three number of equivalence classes, we can construct the state FA for the same language having the three number of states, and this is the minimum state DFA. So this is the one way to prove that whether the given FA has minimum number of states or not. Although determining the number of equivalence class is not easy job, for some complex language, for identifying the number of equivalence class may be difficult task,